In strike-slip tectonics, not only main strike-slip fault strands, but also other structures form at the same time, synchronously. These structures can be confusing because sometimes they have very different kinematics than main strike-slip fault strands, um, or different orientation. So to understand how these differently oriented structures, first order and second order fractures, form within a strike-slip fault zone, rock mechanics experiments and sandbox experiments basically help us with understanding how these different oriented structures form during strike-slip deformation. So in this experiment, they used two wood blocks or two steel blocks, two blocks representing rock formations at deeper levels, and then cover the surface with a clay cake or gypsum powder, some kind of soft rock, represent some kind of material that represents soft rocks in the uppermost crust. So this is a horizontal layer, as you can see. Let's say this is the younger sediments cover the surface of a region, and underneath those younger sediments, we have basement rocks. We can be crystalline rocks, metamorphic rocks, some kind of hard rock. Okay. So in this experiment, what they do, they slowly move one of the blocks in one direction to create this strike-slip motion. As they move this block, the left block, in this direction towards us, and push this right block away from us to create this left lateral strike-slip motion, what they observe a parallel set of first order and second order fractures form within the strike-slip fault zone. So let's see that in action first, then we can discuss how they form and what orientation they form. So in this experiment, it's a structural geology analog modeling experiment. They have a more competent layers underneath gypsum powder, and as they move these blocks, we'll see what will form at the top gypsum powder layer. Now they are moving this upper block slowly. As they move it to the left, which means now we created a left lateral fault, you can see all these first order fractures formed at very low angle to this main strand of strike-slip fault. So where is the strike-slip fault? Where this motion occurred. So if we draw an imaginary line, it should be somewhere here, right? Imagine there's one big strike-slip strand going in this direction from left to right. That's our strike-slip fault. And if you look at the orientation of strike-slip fault, let's add directions. This side will be west, this side will be east. So we have a west-east or east-west strike-slip fault. And let's look at the orientation of this first-order fractures formed during this motion. So they are not east-west oriented. They are actually east-northeast oriented, and they are perfectly parallel. Look at this fracture here. Look at this one. They are perfectly parallel planes formed during the early stage of strike-slip motion. So we call these first-order fractures formed during strike-slip motion redoubt shears. Redoubt shears, R I E D E L, redoubt shears. So these redoubt shear fractures are very special type of structures that help us to determine what type of strike-slip motion occurred in the region. Right now in this experiment, you cannot see a strike-slip fault plane because it's covered with this most recent sediments. In this case, it's gypsum powder. So we don't see fault point itself, so we can't measure the angle of the structural fault. We cannot even unless now this is because this is an experiment. We can observe which side moved in what direction. But in reality, when you work in a project where you have strikes of tectonics, you will see the last scene of the movie, end of the movie, right? After all these things happen, you will find these fractures in the field. And because the actual structural fault is not exposed at the surface, all you have in order to determine sense of slip and kinematics of this event is this first order fractures. So how can I use these fractures to understand is it right lateral or left lateral of structural fault? Let's rewind this movie a little bit and see as we push this block to the left and create a left lateral stress of motion, which direction all these first order fractures are tilted. They are all tilted to the right in the opposite direction of sense of slip, right? So that means this experiment shows us that when we have this, so when we have a left lateral structural fault, first order radial shear structures will form as low angle to the is fractures at low angle to the main strand of the structure. Okay. So let's spend some time on this block diagram and see, other than orientation of these first order structures, what other information we can get from this block diagram. So this tick mark, the shorter lines on one side of this solid line indicates the direction. So here, in this case, we have a mini graben structure, another normal fault here. We think this structural fault zone we created normal faults, extensional fractures. Let's move to this figure. We because these fractures, as you can see in the experiment, they form in perfect parallel alignment like these benches in this photo. We use some specific terminology to express their orientation and alignment. So on this figure, you can see if you assume this is the main slip strand, all these benches are tilted to the left in this direction. If you stand here and observe this radial shear fractures and main strand forming them, they are all tilted to the left. Because of that, we call them left echelon radial shear fractures or left en echelon fracture arrays. Another way, first we check the tilting direction. If they are all tilted in the same direction, in this case to the left, you can start from one end of the fracture and follow the fracture. In order to jump on the second fracture, you have to jump onto the left. Start from this end, follow the fracture, you have to jump to the left. So for each fracture, first order fracture, you have to jump to the left, which makes it, again, left an echelon or left echelon fracture array. If you look at this image, look at these structures, they are all structures are all tilted to the right. If you start from here, follow the fracture, you have to jump to the right. You have to move to the right. You have to move to the right in order to be on the adjacent fracture in the same orientation. So that makes it right an echelon fracture array. Okay. So if you place this stress ellipsis on this image, here this outgroup was compressed in this direction and extended in that direction. If this is the compression or maximum compression direction, in the, and this is the orientation of main fault strand, this maximum compression direction coming from this side oblique to the strike of the fault will push this part of the fault um, strikes the fault blocks to the left, and this side will be pushed to the right. That makes it left lateral strike-slip fault. So if I repeat, in order to form these extensional features here on this outgroup is extended in this direction, uh, which is perpendicular to the strike of the structure, um, and in the direction of depth. So this is the extension direction, or in other words, extension direction on the outgroup gives you direction of minimum stress, sigma 3. In this direction, stress ellipse will be elongated, and in the direction of compression, it will be compressed. And if you remember from earlier lectures, these principal stresses are mutually orthogonal. That means there will be 90 degrees angle between two principal stresses. If you have sigma 1, sigma 3 in this direction, sigma 1 will be at 90 degrees to that. So this is the orientation of sigma 1, and this is the main strand of the strike-slip fault that form these extensional features, parallel fracture arrays at the surface, like we just watched in experiment on YouTube. So as a result of the orientation of sigma 1 in this direction and sigma 3 minimum stress in this direction, this side of the fault will move to the left because this block will want to escape from this maximum compression. So if you push this block from this side, there's only one way to escape from this maximum compression. It is this way, to the left. So if you push this block in the same orientation from here to northwest, then this block will also escape from that maximum compression direction to the right. So that will make it a strike-slip fault. Here we have surface rupture of San Andreas Fault after 1983 Southern California earthquake. And you can see on one side we have North American plate. On the other side to the left we have Pacific plate. But these two plates are moving relatively. As a result of this motion, at the surface we don't have the fault scarp. We don't have exposed San Andreas fault plane. Instead, we have those fracture arrays, which are left echelon ruptures. So if you look at these fractures, they are all tilted to the left. Also, if you start from one tip, follow the structure, you have to move to the left. Follow the structure, you have to move to the left. First, check the tilting direction. Are the structures of fractures, ruptures tilted to the left, right? Then also you can try this following fracture and jump onto the next fracture practice to confirm that you got it correctly. Okay. Here we have another example. This is the sister of San Andreas Fault in another part of the world, North Anatolian Fault that separates Anatolian plate from Eurasian plate. And as a result of very complex regional tectonics, this North Anatolian plate is also in on the right lateral strike-slip. Here you can see left initial ruptures at the surface. This is one here, another one is here, so you have to jump to the left. And there's another one on the left. So with these left initial ruptures at the surface, we can basically determine that slip along this fault plane occurred as right lateral or textural strike-slip motion. So this is how it looks like on the map view. This is North Anatolian Fault as Arabian Plate collides with Eurasian Plate. This poor Anatolian Plate is squeezed like a balloon in between these two colliding plates. As a result of this collision, this whole Anatolian Plate now extrudes to the west, and then there's a subduction zone in Mediterranean Sea. So this Hellenic arc is a subduction zone. So this plate changes direction from west to southwest because of the subduction free zone in the Mediterranean area. And as a result of that, the Anatolian plate experiences what we call escape tectonics. It escapes from collision between these two major tectonic plates. As a result of this motion, just imagine you squeeze this balloon slowly and steady. So these two plates slowly moves towards each other and push this block little bit every year and every year. As a result of the strain accumulation along the uh, northern Anatolian plate fault, um, regularly there is a great earthquake along the North Anatolian fault. So initially, this North Anatolian fault wasn't this big. It was a smaller segment. It's like a zipper started from east and basically torn entire Anatolian plate to the west with progressive progression of these seismic events from 1939 to 1999. And here, how these earthquakes can be so devastating for people. It affects human infrastructure and damages houses and everything. So similar earthquake is expected in the West Coast. So here on this image, you can see redoubt shear structures and other type of structures form in this clay cake experiment. So here we have a cartoon 3D block diagram of the experiment. We have two wood blocks and clay cake on the top. As we push one of the blocks in one direction, there will be this parallel set of fracture arrays formed in the center, at the top within clay cake. So first order fractures will be at very shallow angle to the main strand of the strike-slip. We call this kind of shallow dipping uh, structures, redoubt type fractures or primary redoubt shear fractures. Progressively, second order fractures will form, and these second order structures will be at higher angle to the strike-slip fault zone. These dashed lines in the first diagram are R prime or second order fractures, secondary redoubt shear fractures. So first one is these solid black lines with same sense of slip with the main strike-slip fault zone. If you look at the strike-slip fault zone, it is a right lateral textural strike-slip fault zone. Within this strike-slip fault zone, as we move this below basement rocks, these first-order redoubt shear fractures will form at the surface. And if you look at the angular relationship between these redoubt shear fractures and strike-slip fault, there's a small angle between strike-slip fault and first-order redoubt shear fractures. Rock mechanic experiments show that the angle between this first-order or primary redoubt shear structures and main strand of the strike-slip fault is half of the um, coefficient internal friction angle, P. And second-order structures are these dashed lines on the same diagram. And if you look at this sense of slip arrows on each side of the dashed line, it is opposite direction. So the main strike-slip fault strand is right lateral, but second-order redoubt shear structures have opposite sense of slip, which is left lateral. So primary redoubt shears primary redoubt fractures will be at a small angle and narrow angle to the strike-slip fault zone. They will have same sense of slip, and second order or secondary redoubt shear fractures will be at a much larger angle to the main strike-slip structure. There will be a steep angle between secondary redoubt shear structures and main strike-slip strike. And also secondary redoubt shear fractures will have opposite sense of slip to the main strike-slip fault zone. Okay, right. So then third structure that can form during the same deformational phase are P fractures. P shear fractures develop after establishment of redoubt fractures due to temporal variations in the local stress field. As we move these blocks in two different directions, some blocks will be stressed, compressed, and as a result of this increased pressure, those blocks will escape in one direction and form along this P um, um, pressure fractures, which still have same sense of slip with main strike slip also. T tensile fractures form due to extension. Some regions will be extensional, and then those extensional areas will form extensional tensile fractures um, in the same fault zone. So if you look at this second diagram, now we have this right lateral structural fault. What should be orientation of sigma 1, sigma 2, and sigma 3 for this image? By the way, this is top view, this is map view, this is not a cross section. This is the top of this block diagram. So in this case, in order to push this side of structural fault to the right, there should be maximum compression coming from side in this direction, right? So sigma 1 should come from side of this block diagram in this direction, and it has to be oblique to the strike. This is the strike of the structural fault. So this sigma 1 should be oblique to the main strand of the strike slip, or sigma 1 has to be oblique to the strike of the fault. So sigma 1 orientation should be in this direction, northwest, southeast, and sigma 3 is minimum stress. So in that direction, blocks can escape, right, from maximum compression. So in this case, if this is the direction of sigma 1, this block should be able to move freely in the direction of sigma 3. So sigma 3 should be in this direction, and it will be also oblique to the strike of the structural fault. Okay? So because we have minimum stress oriented oblique to the strike in this direction, northeast, southwest, this block can freely move in the direction of sigma 3. And for strike slope tectonics, we know that sigma 2 must be vertical. So in this case, sigma 2 will be towards the screen, the computer. So if we know orientation of sigma 1, sigma 3, and sigma 2, under this stress distribution, we can also estimate what other type of structures can form. Because if you remember, tensile fractures will form parallel to sigma 1 orientation, and they will open up in the direction of minimum stress, sigma 3. So if this is the direction of sigma 1 here on this block diagram, on this map view, so then this is the orientation of sigma 1. Sigma 1 will basically give you direction or strike orientation of tensile fractures. So they will be all aligned parallel to sigma 1 orientation, and they will open up this gap in the direction of sigma 3, which is consistent with the first diagram. So now I know in what orientation I can expect to find tensile fractures in this region. Why this is important? Because maybe some of these tensile fractures will be conduits for hydrothermal fluids, and they will be forming high-grade mineralization trend. Or they can be fractures that open this gap and result in petroleum migration. So it can be a problem. I need to know in what orientation rocks are form tensile fractures. So other than these tensile fractures, another structure that can form folds. So fold axis will align perpendicular to maximum compression. So that way we can also estimate what will be orientation of fold axis in the same region. Stylolites, here this figure is cutting off some of it. So Stylolite is the complete term. Stylolites are pressure dissolution structures. When rocks, especially carbonate rocks, are under great amount of pressure, chemical bonds will be broken and formation fluids will escape, and as a result of dissolution under pressure, some part of the rock will just dissolve and it will go away. So what will left after dissolution is suture-like fractures will be left on the outcrop. So when you find these suture-like fractures on a carbonate outcrop, that means some part of that carbonate rock is gone because of dissolution. So these dissolution structures or tip of suture-like fractures align with sigma 1 direction. So this little kind of triangular, tip-like structures are all parallel to the direction of sigma 1. Also, on map scale, on map scale, from small scale to map scale, if you know orientation of sigma 1, orientation of sigma 3, you can estimate in what orientation and structural architecture normal faults, reverse faults, detachment faults, truss faults, or faults will align in your project area. All the faults, larger scale, regional scale faults, will be uh, aligned perpendicular to sigma 1 maximum compression, and normal faults will spread out lithological units in the direction of sigma 3, right? And reverse and truss faults, compressional structures, will form in perpendicular to the direction of maximum compression, sigma 1. So that way, all together, just by using without shear fractures at the surface, you can start from small scale, go to outcrop scale, and you can even get some conclusions about regional scale. Here we have a cover image published in GSA Geology journal. This is Christchurch earthquake in 2008 in New Zealand. You can see surface ruptures are very obvious. They are all aligned in the same direction. And here also we have another set of fractures. So these fractures has a lower angle to the main strand of the strike-slip fault, which is going in this direction. So these structures should be primary redoubt shears in this direction, and this other set of fractures which are basically in higher angle or greater angle to the main strand should be second order fractures. By looking at the orientation of fractures, all of these low angle to the main strand structures are tilted to the left, right? So that means this fault plane should be a right lateral structure.